Hi folks, thanks for coming. I think we'll begin. My name is Kerr. I work on the Windows team at Microsoft. This is James McNellis. He's from the Visual C++ team. Yesterday we had a talk introducing C++ WinRT, our new standard C++ language projection for the Windows Runtime. And today we're going to discuss how we're using coroutines to turn all the asynchronous behavior in the Windows Runtime into a far more effective programming model, and also just taking everything that's concurrent about Windows, the thread pool and so on, and making it accessible to coroutines. James.
Yeah, so how many people here were in our talk yesterday introducing C++ WinRT? All right, good, a fair number. How many people attended at least one of the coroutine talks today?
Nice.
And keep your hands up if you've been to two of them. Wow, so we've got a lot of people here for a third round. You know, you survived the suspension points for lunch and the keynote and breaks.
Incredible.
So
it's reliable.
It is, yes. Mm-hmm. All right, so just a quick note before we begin. I know a lot of you then have seen this, but we, the Visual C++ team, are very interested in your feedback and to learn a bit about how you use C++. So we have this survey, and if you fill it out, I'm told that you can win an Xbox One S. I was told I cannot win the Xbox One S, so I hope you do. All right, so we're going to jump right in.
Yeah.
So briefly, this is what it looks like trying to produce async operations today, right? So you'll have a function that returns, for example, a std future, and then within that, you would use std async to go and schedule some work on a background thread, and then you would run all of your hard, expensive computational work on that background thread, and then return the result through that future. And consuming async operations looks a bit like this. So in our consume function, we'll print out that we're about to start the operation. We'll then go and start the operation, but the only way that we have to use the future after that is the synchronous blocking get, and so we'll do that, and now we'll be blocking this thread too, so much for asynchrony. And then we'll print out the result. Now if we want to do continuation today, we'd have to do something like this. So our consume async would actually have to start its own async operation to go run on another background thread, and it would call produce async and do the blocking wait there. So now we've got 3 threads, but at least we've freed up the original thread, and we're just blocking some other thread from making progress. So ideally, the solution here, I think, is future.then, which leads to some beautiful code like this. This is actually very simple code. For those of you who were in my talk this morning, we showed the example that tried to do a loop asynchronously. But so anyway, this is not particularly pretty, and it's also not particularly efficient because of how future.then has to actually be implemented. So async with C++ WinRT and coroutines looks a bit nicer. This is effectively how your synchronous code would look if these were synchronous APIs, right?
Very nice.
You get the file, you open it, you decode it as a bitmap, etc., whatever else this program is doing. Yes?
Doesn't it have to be a co-return?
Doesn't have to, yeah, it would have to be a co-return.
Yeah.
Yes, thank you for the clarification.
Well,
We've
that works today, but yeah.
Yeah, so the specification of what the keywords look like and whether you need to use like a return or a co-return has changed over time, and Visual C++ still supports some of the older syntaxes, and yes, we support the new one too, and definitely use that. This one slipped through in our 300 slides that we've been working on. Yeah.
Sorry about that.
Yes. All right, and so if we look back at our simple example, our continuation looks much simpler, right? It looks effectively like the blocking wait, except now we have a co-await that's non-blocking. Additionally, we don't actually have to use std future for this. We could use another type for encapsulating work. So for example, in the Microsoft implementation, we also have a concurrency task type, which is part of the PPL library. This has some extra efficiency improvements over std future, especially on the Windows platform, where we can utilize some knowledge that we have about the underlying platform and thread contexts. And so, yes.
Yeah, we think we have something better though.
Yes.
Specifically when you're using C++ WinRT. But we'll get to that now in a moment as we show you how that all works. Why don't I use that thing? So first up, however, we want to make sure we can cover the scenario where you just don't want to have any concurrency at this point. Perhaps you want to just block you running a console app, unit test, whatever it might be. So we do provide a .get method, which is very analogous to std_futures get. So if you do want to just block and wait for that result, we certainly allow you to do that. Essentially what we do, so if you were here for our talk yesterday, you'll understand how WinRT interfaces are basically aggregated together at compile time. But conceptually, we'll add a get method to all of the async interfaces so you can make that call, and it'll return the result of the get results method if it's an async operation, or it'll just return void if it's an async action. Just as a matter of course, the implementation happens to be very efficient. So to begin with, we make sure that given if the async operation has in fact completed, we certainly don't want to suspend or even suspend the OS thread. We simply return and you can carry on. On the other hand, if we do need to suspend, we take advantage of the operating system's lock-in condition variable primitive. So this is just a standard condition variable concurrency pattern, but it's provided by the Windows operating system with what we call a slim reader writer lock. And so essentially, the completed handler, which is part of the WinRT async pattern, is provided with a lambda, which will acquire the lock, set the completed variable, and then wake the calling thread. Meanwhile, on the OS thread that's blocking, we also acquire that lock. We then atomically sleep and release that so that the completed handler can acquire the lock and set that variable. Eventually, it'll be erased from the sleep and return, and so you can keep going. So that's our blocking suspend, just as a matter of course. It's very efficient. If you need it, it's there. But really, we want you to go from this produce.get to a co-wait produce. This is a cooperative wait, essentially the same thing. You see the code is very similar, but this is the model that allows us to do a lot of more concurrency, and that's really the focus of this talk. James.
All right, so we're going to talk a little bit about asynchronous operations in the Windows runtime. So starting in Windows 8, when the Windows runtime was made a part of the OS, one of the philosophies that they used to guide it was that any operation that would take longer than you would want blocking the UI thread would be an asynchronous operation. And so all of the I/O is asynchronous. All of the heavy parsing operations are asynchronous. Certainly any network operations are asynchronous. So there's a lot of asynchronous functions. And they have some base interfaces that provide access to these. And so one of these is async info. And the two key pieces here are that it allows you to get the status. So it'll tell you if it's completed, if it's still in progress, if it's been started. And then it also allows you to cancel the operation if it's in progress, or request cancellation. And if you have one of these interfaces, you can just use it like any other COM interface. So for example, if you get an async info from somewhere, then you can call get status in order to get the status, and then you'll have to release the async info pointer when you're done with it. In C++ WinRT, we project this into a much simpler, a much more C++ friendly form. And so here's the async info definition from the C++ WinRT projection. One thing that's obviously notable is that the status function now just returns you the async status. You don't have to pass it through an out parameter. That's, I think, the fundamental thing there. Here's an example of using this. So if you get an async info, there's no pointer involved. You just get the object. You can call status on it, and then when the async info object goes out of scope, it'll automatically take care of the reference counting and the release. So there's 4 different kinds of asynchronous things in the Windows runtime, and they fall into 2 categories. So the first category is async action, which is used to package up a task that returns no result. So here you can see that in the getResults function, which returns void. Tasks that return results are wrapped up in async operations, and so that's a template because it can return various things depending on the API, and it has a getResults function that returns the actual thing. Additionally, there are 2 interfaces that allow progress reporting, and so each of these works just like the similarly named interface, except they have 2 extra functions that allow you to get and set a progress reporting handler so that the producer of the API can tell you how much progress it's made, how much work it thinks is left to do, and then you can consume that and print that out or use it as you see fit in your application. Yes?
What is the template parameter key with the progress?
It's the progress type. So that'll be the type that'll be passed into the handler. And we'll see that a bit. We have examples showing how they work. So here's an example of the difference between them. So we have, for example, get file async. Obviously, it's going to get a file, so it has to return you the storage file. And so that is an iasync operation, whereas a file rename operation doesn't actually return you anything that you can use, and so that's an iasync action. Here's an example showing how progress reporting works. So this is an example that doesn't use progress reporting. We go and we open up an RSS feed, and then we iterate through the items and print out the results. But that function is actually an iasync operation with progress, and so we can hook up a progress handler if we'd like, and here's how we do that. Instead of co-awaiting directly on the result of the retrieve feed async, what we'll do is we'll take the iasync operation and we'll store it in this local async variable. We'll then sign up for the progress notifications by calling the .progress setter, and we'll pass it this function that'll just print out the results. And then we'll actually do the co-await. And so by doing this, we'll end up with something that looks like this, where it prints out the progress, letting us know how much progress it's made reading the RSS feed, and then it'll print out the results at the end with the loop that we had before. On the other side, in the production of this progress information, here is a little structure we can use for progress reporting. We're just going to report the number of bytes retrieved and the number of bytes that we expect to retrieve. And then within the function, we'll get a progress reporting token by co-awaiting on this getProgress token that we'll see a bit later. And then in our loop, we'll download the next chunk or do whatever we need to do, and then we'll just invoke it like a normal function. Cancellation is implemented in the same way. So at the beginning of our function, we can get this cancellation token, which will return us a canceled predicate. And so we can query this, and it will return true if cancellation of the operation has been requested, false otherwise. And so then in our loop, we can actually just check every time through the loop, have we been canceled? If so, then okay, we'll be polite and we'll stop executing. And in our application, what we'll do is we'll start this operation off. We'll then wait a couple of seconds to let it tick a few times, and then we'll cancel it. And then that cancellation will feed into that async operation, and we will stop the operation. And so this would print out something a bit like this. It might vary based on thread scheduling, but it would look about like this.
Great.
So,
wonderful. So,
yes?
This may be a tangent, but how do you co-await directly on seconds?
Yes, we'll actually show that in a bit.
We'll get to that, yeah, for sure. Right, so what we want to do is, the first thing we need to do is we need to make the WinRT async types awaitable. So if you can imagine a coroutine called produce, now we co-await on that, and we eventually get a result back and we want to print it out. What does the compiler actually want to do with this? Well, one option is for, the first thing we'd have to do then is get the async operation that produce function returned. And we check if the operation is actually ready, if it's completed. In that case, we simply skip the suspension and go straight to await resume, which will return the value or raise an exception depending on what happened with that operation. If it was not in fact ready, it'll call the await suspend function, and that's where we can call that completed handler to set up a callback that'll execute once that happens, so that we can then resume the coroutine at that point, and then suspension occurs. Another option is to use operator co-await. So in this scenario, you might imagine that you have some type like async action that doesn't in fact have these three methods, and so we want to adapt it to work in that fashion. It might be just because you can't add those methods to somebody else's type, you don't want to, and so on. But it's up to you. There are two options for that. So what you can do is you define a type that adapts it, and then you define the operator co-await that takes the async operation and wraps it in an await adapter so that the compiler then sees something that it can actually await on.
One of the other advantages of using the adapter is we can reuse the one adapter for many different types if necessary.
Yeah, that's right. Yeah, we have 4 async interfaces in the Windows Runtime, and so we can have one await adapter that deals with all of them. So await ready, what does that look like? Well, for these WinRT types, we simply call the status method, which returns the async status and tells us whether it's completed. If it is, we certainly don't have to suspend. Not ready, well, this is where it gets a little bit more interesting. Await suspend, what we want to do is we want to make sure that we can capture the calling thread context. So we call this co-get-object-context function. It's not a great name for the function. We're really capturing the thread context, not the object context. But that iContext callback interface allows us then to call another stateless lambda at some future time to then throw some work back on that originating context. So here we have the first lambda, which is passed to the completed handler. And what that does is, when that's finally called, it signals that that async operation or action is completed. And so we call context callback to then resume the coroutine back on the calling context. So this is very important if you're writing a UI app. You want to make sure that after your suspension point, you're back on the UI thread so you can update your buttons and whatever else you're doing in your application. When resumed, await resume is called, and we want to call get results. At this point, we know that the operation is completed, either successfully or with failure. And in both of those cases, we want to make sure that we get the result back. So if it's one of the async operation interfaces, we'll actually have a return value. If it's an async action, it returns void, but thanks to generic programming, we can use auto here, and it's one of the few places you really want to use auto, but certainly this is a great example of that. But the other scenario is that it actually, the operation actually failed, and there was perhaps an exception thrown within that other coroutine that you waited upon. And so there's two scenarios there. One is you call the .get method I introduced earlier. And this is what you might call synchronous exception handling. The get method, as you would expect with stood future, will actually throw the exception if a failure occurred. And you can naturally catch it here with a catch block. What might be less obvious is that you can do the same thing with co-await. Now this is not asynchronous exception handling, it's just cooperative exception handling. It's really the same thing as we saw on the previous slide, because the await resume function is where the exception is thrown through. And at that point, you're back on the calling context, so it's just a regular exception being raised. There's nothing exciting there, but it does mean you can handle the exception within a coroutine, or you can allow it to propagate up through many, many other coroutines and handle it wherever you'd like. It's a very natural programming model either way. James.
All right, so what do we have to do in order to make these Windows Runtime async types usable with coroutines? So the first thing to note is what makes it a coroutine type to begin with. So for example, this iasync action type, we have to go and implement certain things for it in order for it to be usable as a coroutine type. And so what we're going to do is we're going to specialize coroutine traits for this type. This is a partial specialization, so it'll work for any coroutine that returns an iasync action. We have similar specializations for the other three interfaces. And if we look at the coroutine lifecycle, just as a reminder from the previous talks, the first thing that will happen is we'll construct the promise as part of the coroutine frame. We'll then reach the initial suspend point, which will ask, should we proceed or should we suspend at this point? We'll then get the return object by calling getReturnObject, which will give us the actual iasync action to return to our caller. We'll run until whenever the next suspension point is. We'll complete either by setting the return void, or calling return void, or by setting the appropriate exception. And then we'll determine whether or not we can destroy the coroutine frame, or whether we should leave it around. So here's an example of what an implementation of iasync action has to look like. So as we said before, we have to implement two different interfaces. There's iasync action, and then there's the basic iasync info. And this is not a complete implementation, this is just a demonstration of the functions that have to be implemented. So the iasync action, we have to actually support the completed handler. And then the iasync info, we have to implement the status reporting and the cancellation support and other things. So one way that we can implement the promise type for this is we can actually just store the iasync action as a member of the promise type. And then in our, so we'll create and we'll hold a reference here as part of the promise. And then in our getReturnObject, we'll return another iasync action that refers to that same async operation action. In our final suspend then, we can just return suspend never. The promise type will release its reference, but the caller will still have its reference if it needs it, and so the object won't be destroyed. There's one problem with this, and if you were in Gore's talk, then he talked about this. And that is that we need two allocations in order to do this. So we need one allocation. We have to allocate the promise on the as part of the coroutine frame, which is going to end up on the heap. And then we also have to call this make async, which is going to allocate an instance of async on the heap as well. So ideally what we'd like to do is we'd like to coalesce these into a single allocation and just allocate the async object as part of the promise. And so here is what we might want to do. We have our promise type actually implement those two interfaces and be the async type. This allows us to have only one allocation. and we have the promise implementation, and we also have the WinRT implementation, all as part of the same class. We run into, however, to some lifetime issues with this.
Yeah, so the problem here is that the lifetime could look like this. So the WinRT async object could in fact have its last reference released before the coroutine has come to an end. Only later will the final suspend function be called, and that's a bit of a problem, or at least that's one scenario we need to deal with. Another lifetime scenario we need to deal with is that the async object outlives the coroutine. So first, final suspend is called, and only later the final com reference is released. So this is called a condition race. Oh, sorry, race condition. So essentially, we need to go back.
I told you they'd find it funny.
I know, it's great. So we need to take a closer look at two things: com's reference counting and the life cycle of a promise type, or the coroutine frame. So firstly, here's a typical implementation of com's reference counting. We have addref and release. Here we're using a std atomic. We increment the reference count in addref. We release the reference count in the release method, and we get the remaining reference count. And if it's 0, we can delete the object. That could be a problem though, because we can't actually delete the promise type. That needs to be destroyed separately because we didn't new it up in the first place. Looking at the promise type, we have two options there so far. So first is suspend never. And that basically says we're going to destroy the coroutine automatically. Go ahead and do that for us. But that won't work because there might be outstanding com references to that same instance. Another option is to say suspend always. But so that essentially says, the coroutine will be destroyed manually. We'll take care of it. But that also won't work because we might not in fact have any outstanding com references, so there's no one to destroy it. So what we need to do is override the release method provided by the implements class template to do a little bit more interesting work. So the first thing we do is we hoist up the just release. We take that decrement operation and we hoist it up as a separate function so that we can reuse it a little later on. If the count reaches 0, we can safely destroy the coroutine because we know that there are no outstanding references. We also have to do a little bit more work though. On the other side, in the promise type, we need to do a conditional final suspend. So instead of doing an always or never, we need to say basically, firstly, release the self reference. So release the reference that the promise type holds to itself. And then if the reference count reaches 0, we know that it can be destroyed automatically. So yes, go ahead and do that for us. Otherwise, no, wait, we'll take care of that ourselves a little later on. So by doing these things, you get to have an incredibly efficient implementation, reducing the number of allocations, and it works really well.
Any questions about that?
Make sense?
All right.
Great.
Excellent. So let's look at how we implement the progress and cancellation. So here's a coroutine that uses both the progress and the cancellation tokens. So first we get the cancellation predicate and the report progress function. And then we enter a loop, and while we're not canceled, we stop running for 1 second. I was going to say we sleep for 1 second, but we won't do that, and we'll see why in a bit. And then we report our progress just to report which operate. Yes?
Why do you co-await getting the tokens?
Yes, we're about to see that.
Oh.
Yep. So the question was, why do we co-await getting the tokens? And we're just about to show that. So then on the consumer side, similar to what we've seen previously, we'll call produce, and we'll store the iasync action there. We'll attach our progress handler, which is just going to print out the number of times we've iterated. We'll then wait for 3 seconds, and then we'll cancel the operation. And what this is going to do is it's going to print out 1, 2, 3, and then we will cancel the background operation. It will notice that it's been canceled, and then it will stop running. So there's 3 different kinds of things that we can pass to co-await. So the first one is the obvious one. If you have a class that implements await ready, await suspend, and await resume appropriately, then you can just co-await that, and those functions will be called as you would expect they would be called. And in the Visual Studio IDE, if you're using that, the co-await operator will show up as blue or whatever your normal keyword color would be. You can also, however, use the co-await operator to transform one particular type into something that is awaitable. And so, for example, if we have a value struct here, it does not have any functionality on it, but we might want to be able to await it. And so we can overload the co-await operator to take a value and return one of those pass-through objects from the previous slide with the actual number that we want to await, provide back to our caller. And so here, yeah.
Is that MSVC extension or is that standard supported?
This is standard supported. Yes, the question was if this is an MSVC extension, and it is not. Everything, well, I won't say that. Yes, but in the Visual Studio Editor, this may show up as teal to tell you that it's an overridden operator. I actually didn't know that the IDE did that because I have custom colors, but Kenny enlightened me to this fact. So the third kind of thing you can await on is via a function called await transform. So inside of your promise type, you can define overloads of this function await transform. And what this will do is it will allow you to customize the behavior for a particular promise type when you await on different types of things. So for example, we're going to use this in order to allow us to await on a tag object like getProgressToken and actually extract state from the promise using that. And so here's how we do that. We define a type named getProgressTokenT. This is just a tag type. You would never name this in your own code. And then we define an instance of it named getProgressToken. And this is the instance that we saw in the previous coroutine example. And then we're going to overload await transform to take an instance of this, and it's going to return a progress type constructed with a pointer to the promise type. And so this allows us to access the promise and return object from within the coroutine. Because if you remember, this is allocated as part of the coroutine frame, and you don't actually get to see it from within the coroutine. It's all behind the scenes unless you do this. So then our progress type is actually going to be implemented quite simply. It's just going to store that pointer to the promise. Its await ready is going to return true because we don't actually want to suspend. We just want to return the progress token back to the caller. Await resume will then just return the progress token. And then we will overload the function call operator so that you can actually call it with the current progress, and it will call the setProgress function on the promise, which will do the appropriate thing for the WinRT interfaces. So the key here is that it's a lightweight awaitable type. It doesn't actually have a whole lot of state to it. It's not going to cause you to do any allocation. It doesn't suspend. It returns the function object, this progress type object, and then inside of that operator, we just notify the listener. And we'll do the same thing for the cancellation token. So here it's going to store the pointer to the promise. The await ready will return true so that we don't actually want to suspend. The await resume will return a copy of this object. And then inside the function call, we're actually just going to ask the status, have I been canceled yet? Any questions about that or how that works? No questions. Is anybody still awake? Okay, there's a few people awake. Good.
Great. So we've talked a lot about how to create coroutines, certainly in the previous talks as well. But at some point, you're going to run out of things to await on. And so you want to create some organic things that you can actually build and do some real work with yourself. And that's where the thread pool comes in. So let's begin, though, with this function. So it returns an async action. And so this is not a great coroutine because it won't actually compile. It must return something. It's just a function. Give me something to return. So one option is to await on something that you can actually await on. This is an existing awaitable type. In this case, we're actually calling an operator co-await for that standard chrono duration, but it's a valid option, certainly. Option 2 is to actually forward an existing implementation. So you have an implementation of async action, you can simply forward that on. And that's just a regular function. But nobody wants to actually implement those interfaces. That's kind of a chore. So we want to be able to integrate the Windows thread pool in such a way that we can get that work done for us very efficiently and very simply. So the Windows thread pool has 4 types of objects that you can actually submit to the thread pool to get work on the thread pool. As a work object, which is basically, here's a callback that you can put on the thread pool to execute at the earliest convenience. Another one is wait, which is basically call me back on the thread pool when a certain kernel event object has become signaled. Timers are another example where you can say, run this callback when a certain timeout occurred or a certain time in the future. And then I/O. Overlapped I/O is obviously the thing that the Windows thread pool was built on and built for. It does incredibly scalable I/O on the Windows thread pool. So the first example is Windows thread pool work. So the example here is, you have this really great coroutine. It does a whole lot of work. There's just one little problem with it. It just lacks a suspension point. So because of that, it never actually gets to the point where it returns to the caller so that the caller is free to do some other work concurrently. How do we solve that? Well, first we need an awaitable type. So one option is to write an awaitable type like this, suspend never. It's not very good though because it doesn't actually introduce any suspension. And then we have this coroutine, which is certainly valid, but it's faulty because it calls sleep, and it doesn't suspend, and so you're actually going to block. So the bottom call in your main function there blocks for however long that is, 5,000 milliseconds. And then, so this assertion actually is guaranteed to succeed. The status will always be completed because by the time it gets there, it's already finished. So that's a bit of a drag. How do we get work on the thread pool? That must be really, really hard.
I think this is going to be like 30 slides worth of stuff.
I think so.
Yeah.
Brace yourselves. And there it is. There's a resume background awaitable type. Await ready says no, I'm not ready. And so it's going to suspend. The await suspend function is then called, which submits the work to the thread pool. And that's the try submit thread pool callback function. There's another more complicated function which allows you to create a work item and submit it multiple times, but in this case, this is all we need. The stateless lambda there then goes and takes that coroutine handle and resumes it, which gets your work effectively on the thread pool in a very simple manner. It's almost as if the thread pool were designed for coroutines.
Almost, yes.
Yeah, almost.
That void star, it's like that void star knew that
yes.
its destiny was to be used for coroutines.
That's it. So we take our original function that does all that computationally expensive work, and all we need to do to get it on the thread pool is to co-await resume background. Prior to the call, you're still on the calling thread context, but amazingly, after the call, you're living on the thread pool. And just like that, you can move work onto the thread pool very efficiently and very scalably.
One function, two different threads.
There we go. So let's look at it is pretty cool. It's worth clapping for. Let's look at another example, so let this really sink in. So here we have a produce function. Again, it's a coroutine. It co-waits suspend never and then sleeps for 5 seconds. So that's an OS sleep. The actual operating system thread will go to sleep. In the main function, we call produce twice. So we have two Async actions. And there'll be a 5-second delay here and another one over here. So that's not a lot of concurrency. What we want to do is co-wait resume background. Now we have a lot of concurrency because that delay is combined down there. And so to visualize that a little bit better, you can imagine there are two threads starting these two different versions of the application. On the left-hand side, you can see suspend never, and you can see that it printed out the thread ID in all of those points through the code, and you can see it never switches threads. It's always one thread, and there are two individual delays there. With resume background, you can see the initial main thread running, but at some point you get a 5-second delay, and then you see those two threads from the thread pool kicking in to do the actual work in the background, and then the main resumes. Let's look at one final example of that. So if you were here for our talk yesterday, you would have seen our example, very cool application. We took an image with some text in it, and the user would pick the image, and it would go to the application where in a background thread, in a coroutine, we would actually do the work of doing some OCR on that image, finding the text, and then returning it to a XAML application where we displayed it on the screen. And that involved essentially these two coroutines. So there was a foreground async, which used the file open picker, which is the thing that pops up the little window, you can select a file. And then when it got the storage file, it would pass to the background async file. Background async did that work, and it used co-await resume background to get the work onto the background thread. So it starts off, you require the UI thread here because you're interacting with UI resources. We then offload the work to the thread pool, and then we're back on the UI thread over here. So thanks to coroutines, this isn't too hard, but I think we can do it a little bit better.
Maybe we could put the functions together.
Yeah.
Yeah.
You think we can do it in one function?
I hope so.
Okay. Well, let's see what we can do. So here we have what I call a thread context. In its constructor, we get the calling thread context, and we capture that and we store it in a local variable, the iContext callback variable right there. And then later on, when that coroutine resumes, it gets the a coroutine handle and then resumes the coroutine on the original calling context. So how would we use this? Well, here's an example. First, we start off on the UI thread. We use the file open picker. We then capture the UI context, immediately switch to the thread pool. We do some work in the thread pool, and then we can return to the UI thread simply by co-waiting on that UI thread, and we finish the job. Done.
This is going to make my on-click handlers a lot simpler, I think.
Yeah, I think
Yeah.
so. What do you think?
Yeah. So, are there any questions about this?
This actually works.
Yeah, it does.
Yeah.
Oh no, yes?
So, are these things part of the headers that are generated by your compiler today, or is this just separate code?
Are these things part of the header that the library that you generate today, or is this separate code?
Yes, that's a good question. So yes, this is part of the base library. So as you saw yesterday, there's a compiler that generates the projection based on metadata, but that's backed by a base library which has all of this stuff in it. So you'll get this for free with the base library. And it's included in the projection.
Yes?
So what if exception is thrown while you're...
What if an exception is thrown while you're on the background thread?
That's fine. What ends up happening is whenever that is resumed, wherever the thread is, it'll get. Wherever the exception is thrown, it'll be caught by the next boundary, and it'll just propagate up the stack. So within here, you could certainly wrap that, like I showed earlier, with try catch block, and you can catch it in here. You could allow it to propagate up, and the async action, which is the return type, that'll be the thing that actually holds onto that exception pointer. So whenever you wait on that guy, you'll get the exception again. So it'll propagate up in whatever way you want to do it for your application. Whether it's catching it here, allowing it to propagate, catching it later, or allowing your application to terminate.
Anyone else? All right, I do want to note that, so while this example used of resume background used the Windows thread pool, it would work with practically any thread pool, since most thread pools either let you pass a C++ function object of some kind or a function pointer and a void star, and that's all you really need in order to implement this.
Yeah, precisely.
All right, so as we said though, work is not the only thing you can put on the Windows thread pool. So you can also put wait objects on the thread pool. So here's an example of a program that does an inefficient wait. So here we have a producer and a consumer. And in each of those, we're going to go and resume on a background thread. In the producer, we're going to go and do some potentially expensive work. And then we're going to set an event to its signaled state. In the consumer, we're also going to resume onto a background thread. And then we're going to wait. So we're going to wait for that event to be signaled. So this is inefficient. Because while we have moved the wait onto a background thread, we're still just sitting on that thread not doing any work. Ideally, we'd like the thread pool to coalesce all the waits, and then as objects become signaled, it will run the appropriate callbacks. And so to support this, we can implement a resume on signal. We have a constructor here that we have two constructors here. One takes the handle of the object to be waited for. The other takes the handle to the object and then a timeout. In our await ready, we just check to see is the object already in its signaled state, and if it is, then we don't need to go through the suspension. In suspend, we go and we create the thread pool wait object, and we will submit it to the thread pool. And this is what will actually tell the thread pool when this object becomes signaled, then go and schedule my continuation, which is going to be the resumption of the coroutine. Mm-hmm. And then in await resume, we actually return a bool, and it will tell you if the wait succeeded or if it timed out. And so we return true if it succeeded and false otherwise. And so here's our inefficient wait again. And we can convert this into an efficient wait by changing that co-await on the resume background into a co-await resume on signal. And so this will now basically stop running that coroutine, and it will schedule the rest of it on the thread pool. But the thread pool won't actually run it until the event becomes signaled. So we're not sitting on a thread just churning, or, well, just sleeping, I guess.
Yeah.
And here's how it would look with a timeout. So we can await a resume on signal with a 500 millisecond timeout, and if it succeeds, then it will return true, and we can use the state or do whatever it was we were going to do. And if it fails, then it timed out, and we do whatever we need to do there.
Great. Another example is the thread pool timer. So in this scenario, you might want to do some increasing delay, perhaps, for a network retransmission. And so we start off on the background on the thread pool, and then we do this increasing delay while we wait for some packets to arrive, perhaps. But this is not very efficient for the same reason. You're hogging a thread pool thread. You're sleeping. That's not an efficient way to do that kind of waiting. So what we can do is we can introduce a resume after awaitable type. Here we have another duration, which is just a standard chrono duration. That's just a type alias in the Windows Runtime. And await ready, it'll see, well, is there any time left that I should actually wait on? If not, then I'll resume immediately. But if there is, we'll create a thread pool timer object, and we'll submit it to the thread pool, and that callback runs, which resumes the coroutine on the thread pool when that time has elapsed. Very straightforward. So we go from our inefficient timer to a far more efficient timer using resume after. Now, there was a question earlier about how do we do that 1 second co-await? And that's simple. What we have is the operator co-await, and you should know this by now. We have basically the conversion, which turns it into an awaitable type using the resume after type I just showed you.
And time span is just a type def for a chrono duration.
Yep.
With the appropriate periods that it matches the OS time span.
Yeah. So you can now literally write something very simple. I want to co-wait for 1 second over here, perhaps 500 milliseconds, and it's a very natural way to write your code if you have to do that sort of work, and it's very efficient. It runs on the thread pool.
So the other kind of thing we can put on the thread pool is I/O, and we're not going to go into this example in quite as much detail as the others, but here, for example, is a coroutine that opens up a file on your hard disk, filename.txt. I'm sure it's got something very important, very secretive in it, yes. And then in a loop, we're going to read chunks of data from that, and we're going to do so asynchronously. And that read function is actually not particularly complex. The only thing we wanted to point out here was basically all we have to do is call read file with the overlap, with the appropriate parameters for it to do asynchronous I/O, or overlapped I/O as it's called in that API's specification. Basically, all of the work that we're doing here is just to convert the parameters into the right form and then do the appropriate error handling.
Just coincidentally over there, the overlap structure is actually allocated as part of the coroutine frame. So it's an incredibly efficient way of handling this, and we take care of that lifetime for you, doing through coroutines.
Cool. So with all those, we should start writing a lot of coroutines that call sleep.
Yeah.
Yeah,
you think? Is it going to perform though?
Is it going to perform? Is any of this going to perform? I don't know. Std future is part of the standard library.
It's got to be good, right?
It's got to be good. Yeah. It's
Yeah. Okay. Well, let's see.
Yeah. So we wrote this. We have this little benchmark here, and all it does is it's 3 nested coroutines. So coroutine 1 calls coroutine 2 and then it waits on it. Coroutine 2 calls coroutine 3 and does the same. And then coroutine 3 just moves to a background thread and it doesn't actually do anything. So what we're really trying to measure here is the actual overhead of our iasync action implementation compared to std future or PPL task, which is the task implementation that most people are using for Windows Runtime programming today. And we have a few little benchmarks. I don't know if you want to describe the benchmarks.
Sure. So we have 3 of them. Get all, as you can see, it runs them all in series and waits for each one. So it calls 1 and then waits for that to finish, and then calls 2, and the next one, and so on, for however many iterations there are. Then wait all, it does the same thing essentially, but it does it in a loop. So first it builds up a vector of the right size, and then it calls 1 for each one to actually create that coroutine. And finally, once it's created them all and actually got them all started, it'll wait all cooperatively using that wait all function. And it'll block at the end of that once you know it's done. Then there's one more, run all. It does co-wait 1. So again, it's going to do them one at a time, but using co-wait, and then it's going to wait at the end of them using the get method. So they're all essentially doing the same thing. At the end of it, you would have had however many iterations running and completed, but they test various nuances of the implementation.
Yeah, so I guess just 2 points. So we don't have all of the fancy enhancements that Gore presented in his talk,
Right.
and we're adding the overhead of COM to this. So does anybody want to take, anybody who I haven't talked to already about this, want to take a guess as to how much more or less efficient it is than std future? All right, nobody. So here's the graph. So these are the results for 1 million iterations. In yellow, we have std future. In the brownish well, I don't know what color that is.
Mustard, maybe?
Mustard,
Yeah.
mustard, Dijon. Has the PPL task. And then the red one is the iasync action. And lower is better. On this graph, the measurement is in seconds. So yeah, so you can see there's a 40x difference in that middle bar chart between stood future and the iasync action. Yes?
I guess my assumption, not knowing the internals, is that Gore's optimizations would have reduced your chain of coroutines to a single return statement.
No, that's not in fact what happens. These are all...
So the question was,
Yes.
with the optimizations that Gore described previously, this should have reduced everything down to a single return statement. And maybe you can answer
Yeah,
that.
so no, because here we're actually building something that can work with the Windows Runtime. So there's actual runtime object here that you can get a reference to. This isn't optimized away in that way. We don't want it to be optimized away because we actually give you more features here. We give you something that you can actually give to another language. This is ABI friendly. You can give it to C# and they can consume it.
So I was going to say the real reason that you can't do that optimization is it has this co-await resume background, which forces that onto the background thread so that it can do that await. And yes, that await is not going to actually do any work, but the transition to the background thread is still essential here.
Yeah. So it can't be inlined.
So yeah, I mean, I guess this is okay.
It's okay.
Yeah. And
It's a first try.
Yeah, so the overhead from future comes in a few places. The first is that when it goes to run a continuation, it has to start a new thread to run that continuation because it doesn't have the appropriate context information to know if it's appropriate for it to run its continuation on the same thread. Whereas we can take advantage of the COM context information to know if I'm already on a background thread and I need to continue running on a background thread, then I don't need to do any thread transition. I can just run the continuation there. And the same thing goes if you're already on the UI thread and you need to run a continuation on the UI thread, then you can do the continuation there. We only have to actually do the thread transition if it's necessary.
Right.
And we're also using the thread pool, not actual, real threads. So we don't have to start up 3 million threads, which is what.
But in the example, those 3 coroutines, they all ran on the Windows thread pool, but it's the overhead of everything else they add on top of that we're seeing here.
So.
Great. Well, thanks for coming. There's some more information at moderncpp.com. You can email me if you want more information about CPP, C++ WinRT, or anything else, and you can reach us on Twitter. And anything else?
Yeah, we have CoroutineCon going today, so we've got 3 awesome coroutine talks. Unfortunately, you've either attended them all or you've missed them. Additionally, Kenny and I gave a talk yesterday at 11 a.m. Embracing standard C++ for the Windows Runtime, in which we gave an introduction to the C++ WinRT library and described, the architecture of how it works, how it tries to do what it does efficiently.
Yep.
And so we'll highly recommend that for when it's available on YouTube soon.
And his boss wants us to mention that link over there. Please do visit that. That would make them very happy.
Yes, and when my boss is happy, then I'm happy.
There we go.
Yeah. And with that, that is the end. So, are there any questions? Oh no. Yes, Gore.
Yes, I would like to clarify that indeed, for your example, there will be no heap allocation. So all of the functions will collapse into one. But there is an indirect call from the OS kernel that compiler does not observe.
Right.
So you will not have any heap allocations, but it will not be nothing because you gave a call to OS and it will call it at some point.
That's right. Yeah. So in the first example, we had the COM object explicitly allocated within the promise type. What Gore is now saying is that because we've combined them together and we actually have the promise type implementing those interfaces, there's one allocation and the compiler says, hey, I don't even have to do that allocation. So that doesn't even occur. Yes, more.
Assuming that you use 0 overhead task type that I showed earlier.
Yes.
The one that has the RAII symbol.
Yes, RAII. That's the trick.
Right. Any other questions?
Is this available now?
Is this available now?
It is not available now. It will. My boss tells me it should be available in a few weeks.
So we're not waiting for VS Next.
No, not VS Next. No.
And all of these examples, like with the library in development, they work with Visual Studio 2015, the released version, and the Windows SDK, the latest released version.
Yeah, and C++ WinRT works on Clang as well. And as soon as we get Clang support for coroutines, this will work too.
You said that you can implement this on any type of thread pool. Will there be the same efficiency internal information.
Yeah, so the question was, we said this could be implemented on any type of thread pool. So that was the resume background can be implemented for any type of thread pool. And the question is, would it be as efficient on other thread pools? That's fundamentally a question for how efficient the thread pool is. It will be as efficient as, say, passing any other function to the thread pool.
Windows just happens to have a very efficient thread pool model that works for us, but I'm sure the other operating systems have something that you could rely on as well.
Any other questions? All right, well, one more from Gore.
So, can you go back to the slide where you were checking cancellation in a loop?
Only if you're not going to complain.
Serialized.
Oh, that one? Yes.
Yes.
So, would it be possible if we ask you nicely to provide a type in the base library, like Async action with progress automatically cancelable, so that we don't have to actually check for cancel at all?
So that at every suspension point, it would automatically. I'm sorry. Yes. So the question was, if Gore could ask very nicely for us to implement a type like iAsync action with automatic cancellation in the library that would automatically do the cancellation for you. And my question is are you saying at every suspend point it would automatically check am I canceled and then do the cancellation?
Yes.
So the end of my question is that would you be able to use await transform to transform every single core await in your function to check automatically for cancellation so that you don't even have to ask for cancellation token and do that?
Yes, that is possible. We can certainly do that implicitly. So that's a great idea, and for Gore, we'll do anything. Yes. Yes.
Well, he's done so much for us.
Yeah.
So yeah.
Yeah, that's a great idea. Yes.
Yes.
So I've seen so far that the operator co-await is always being done as a free function. Can it be a member function to, I don't know, like does the
Yes.
conversion stuff that is usually initiated, like is that?
Yep,
Okay.
it can be a member function.
Okay.
All right, well, yet one more.
have an already asynchronous function, and there, inside this function, there are a lot of awaits in there. And if we just throw away those awaits and replace them with .get, what performance change?
Yeah, so the question is if we have a function that has a lot of co-awaits in it, like we had the example at the beginning that was just like co-await one thing, co-await another thing, co-await another thing. What is the performance overhead if we just replace those with .get, so if we make it synchronous? The performance overhead is effectively that now you've turned that asynchronous program into a synchronous program, so that function will sit on the thread basically doing nothing while it's waiting for those synchronous operations to complete. That is generally not going to be more efficient if you are dealing with, for example, I/O, which almost all of those functions dealt with. Mm-hmm. Right, because now you've just got a thread that's sitting there not doing any work, whereas the OS could be using it for something else. So, all right, well, thank you everyone for coming. And
Gore.
Gore.
So when C++17 is implemented in your compiler,
Subtle.
Well, we support both Visual C++ and Clang, so.
would you add no discard to Async action in this program?
What is no discard?
Compiler will complain bitterly unless you call await on that type or stash it somewhere.
So it's like check return in Sal. Yes, yes, sure. So the question was, would we be willing to annotate these functions so that you actually have to await on them and not just like, or .get on them. And yes, we would absolutely consider doing that.
Yeah, so the focus of yesterday's talk was showing you how all of this is done in standard C++. And we're all about embracing standard C++ for this language projection. So anything, as the language improves, we want to improve. As new features are added, compile them that we can rely on, we certainly want to take advantage of that and make them available to you.
All right, and with that, thank you all for coming.